Let's see, this is chapter 14. Beginning with number 1. So which of the following is a conjugate acid-base pair? Remember what it takes to be a conjugate acid-base pair. When you look at, for instance, hydrochloric acid, when it reacts with water, what happens? Proton transfer, right? That goes over here. So that means this is the conjugate base. And that is the conjugate acid of this base. Because it's the proton receiver, acceptor. And this is the proton donor. Okay? So it makes this the conjugate base of that acid, and this makes that conjugate acid of this base. So when we say, when the question is acid-base pair, we could say this one, right? That's an acid-base pair. This part of the molecule is the same on both sides, only this one's missing a hydrogen. You can only miss one hydrogen in a pair. Or we could say, that's an acid, and its conjugate base would be this way. Because going back the other direction, that would be the proton donor, and this would be the acceptor, and this would be the conjugate base of that acid. So it works both ways because they're in equilibrium. So out of those choices that we have, which one gives us the core of the molecule on one side, on both sides, and then only a proton difference between the two? How about that one? All right. One proton difference. So this would be acid, that would be the conjugate base. Right? That's number 1.
Gratitude. Construction is terrible
Where's that?
on the interstate, which is from sandstone.
Where?
From sandstone here.
Um,
And they're doing it right there on the bridge at Sandstone, you know, the exits are, and then the other bridge
yeah, that's right.
all the way to Beaver.
Oh, that's right. You come off right there at the New River. Okay, number 2. A hydrogen sulfate or bisulfate ion. HSO4 minus. That's one of your polyatomics that we learned early on. It can act as either an acid or a base in aqueous solution. So if it acts as an acid, what would be the proper equation? Well, in aqueous solution, the only thing it's got to react with is water. Well, excluding its neighbors, of course. So when it reacts with water, if it acts as an acid, it's the proton donor. Right. So now you have left this one. Right. So there's the conjugate base, and there's the conjugate acid of this base. So which one is that? D? Yeah, D looks like a good candidate. What if we said, if it can act as an acid and a base, let's just say, all right. If it's going to act as a base, what does it do? It donates a proton, right? So it donates that proton here. So what's, oh, excuse me. That was dumb. It accepts a proton. So it takes a proton from water. And if it accepts a proton, what does that leave us? Right? OH minus. Okay, so that would be the other way that it could go. We did acid first, this is base. The answer to the question as given is D, of course. But if it were acting as a base, then A would be an answer. Right. Number 3. Which of the following is the equilibrium constant expression for the dissociation of a weak acid HOCl? What's the name of that acid?
Hydrochloric.
Folks, this is hypochlorite, excuse me. Got a brain fart. Hypochlorite would be this part of the molecule. So H become us, be hypochlorous acid. What if I substituted sodium for that hydrogen? You just got through using it. That's bleach. Sodium hypochlorite. Okay, back to the question. Equilibrium expression for this dissociation. All right, you can tell from the choices that we're using an abbreviated form. Right? We're not reacting it with water. We're saying this and that. Right? So the K for this one would be products over reactant. Like that. And the answer to that would be A. Okay. That was number 3. And let's see, we'll skip a few, come down to 6. A solution in which the pOH is 12.1 would be described as acidic, neutral, or basic. All right, so pOH is 12.1. I don't think in terms of pOH, I think in terms of pH. So if we say, what's the pH? That's equal to 14 minus 12.1 would be what? 1.9? Right, that's definitely strongly acidic, very acidic. Okay. That's just the way my brain works.
So.
Yep.
Can you tell me the pH ranges? Is it?
This is neutral. Right. And then acidic is if it gets less, down to 1, and basic is it can go up 14. Actually, it can go less than that, but for the creator of the range, Sorensen wasn't interested in anything less than about 2 or 3. But it's a negative log, it's a calculation, it's a mathematical formula. So anything's possible. As long as you know what the hydrogen ion concentration is, you can calculate a pH. All right, let's see, that was 7. Which of the following indicates the most basic solution? The most basic. All right, we've got apples and oranges here. If the first one is 1 times 10 to the minus 10, 1 times 10 to the minus 10, hydrogen ion concentration, what's its pH? pH 10, right? Okay. pOH is 6.7. So pH would be, let's see, 6.14, 7.3, right? That would give you 14. Right? C, OH minus, 7 times 10 to the minus 5. 7 times 10 to the minus 5. We can calculate that one. Should take just a second. Calculate POH and subtract it from 14. Oops. Hit mine. There we go. Take the log. Change sign to 0.15. So POH equals 4.15 and pH equals 9.85.
So to get the POH, you just do the negative log of the 7 times 10 to the negative 50. Okay, I just wanted to
Yeah.
make sure.
Yeah, exactly right. Let's see, pH is given 4.2 for the next one.
And that gives POH, right? That negative log.
Yes, negative log of this is POH, and then I subtracted it from 14.
And then negative log of just the hydrogen concentration equals straight pH.
Yes. Uh-huh. And E, at least 2 of the solutions are equally basic. Okay. Well, do we have any that have the same pH? No. Right, so it can't be this one. So what's the most basic? The one with the highest pH. Right?
Why isn't it
Yeah, why isn't it A? It is A. Sorry. You're right. Right. 10 is greater than 9.85. Get that in my head. All right. Let's see. Number 8. Which of the following solutions contains the strongest acid? Okay, strongest acid. In this case, we've got one of those acids is diprotic. So which one controls the pH for that solution? It's the first one. So you only have to focus on the first Ka, Ka1, and compare that to the rest of them. The strongest acid in chemical terms is the one with the largest K value, because large K means further to the right, which produces protons. Right? So the largest one out of that whole group is hydrofluoric acid, 10 to the minus 4. Okay. How about what if I got sneaky and changed the question and ask you which one contains the strongest conjugate base? In that case, you need the weakest acid. Right. Now, the monoprotics are fine. The weakest conjugate acid would be, if we just compare the first Kas, would be A, hydrocyanic acid. But that diprotic acid is going to produce some C6H6O2 2 minus, right? The second one. This H2 C6H6O6 will produce this plus this, and then that will produce an even weaker, an even stronger base, excuse me, C6H6O6 2 minus. So there will be some of this in the solution. There won't be much, right? Because the K is 10 to the minus 12. But still, if the question is the strongest conjugate base, that's your answer. Right there.
It would be
Yeah, yeah, it would produce the strongest conjugate base. Simply because it goes through these two, produce that one, and then it would produce this one. And this is the strongest base of all because that's a weaker acid. 10 to the minus 12. I mean, if you really wanted to hammer it down hard, you could calculate the KB for each one of these. Right, and that would tell you, and the largest KB then would give you the answer, but this is quicker. All right, number 9. Which of the following statements are, should be are true? So if only one of them is true, it should be is true. How about the pH of a strong acid is always lower than the pH of a weak acid? Is that true? We had an example in the lecture of hydrochloric acid.
Yeah, because the lower it is, the higher the pH, right? Or the lower.
Yeah. The lower the hydrogen ion concentration, higher the pH, makes it more basic. In fact, that 10 to the minus 10 hydrochloric acid example we had in our lecture gave us a basic pH. So just because the acid is strong doesn't mean that it has the lowest pH. It's also concentration dependent. All right, so A is false. B, the pH of a solution can never be negative. That's false. Yeah, it can be negative, right? If I had 10 to the first power concentration of hydrogen ions, and I did a negative log, that would be -1. All you need is one example to falsify it. It says never negative. All right, I got an example that proves you wrong. C, for a conjugate acid-base pair, Ka equals 1 over Kb. No. Ka equals Kw divided by Kb. So all three of them are false. Now, can you imagine a way to change those around so one or more of them can be true? Think of it in those terms. Just because you got the right answer on this one doesn't mean I can't change it. Right? Sneaky. All right, number 11. For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? All right, so we can write conjugate acid-base pairs for each one. PO4. So its first proton dissociation would give you this, that, acid-base. We lose one proton. That means the positive charge leaves and leaves behind a negative. And then we take this one and strip off another proton, right? Then we take the last one and strip off the last proton. Right. So those are your possibilities. And it looks like D is the only one that works. It's not a conjugate acid-base pair, right? The first one, it's true. It's this one. That's A. B is this one. C is this one. And D is false because you're stripping off 2 protons to get to PO43 minus. Can't do that. And just to drive home the point that when these things are in aqueous solution, H3O plus and H2O are always conjugate acid-base pairs in aqueous solution, whether there's an acid there or not. Okay, that was 11. see, what am I going to next? 12. Let me see, I forgot to mark Katie. I assume she's on her way.
Yeah, she said she'd be here for the lab.
Okay. For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? All right, if you got diprotic acids, if the K1, right, for the first proton and the K2 for the second proton have similar K values, then the second one will affect the pH. We've only looked at, in fact, I don't know of a single one that would work that way. This is hypothetical. So which one of these is close enough to affect, right? The first one is 5 orders of magnitude difference. That's not going to have anything to do with it. Second one's 4 orders of magnitude. C is another 5 orders of magnitude. D is they're almost equal. Like maybe the second one is maybe half of the first one. So D would be the one where the second dissociation would affect the pH. Now, I'm not going to have you do any calculations with those. It's just to recognize that's the case. Because most of the time, A, B, and C are the real world. All right. Let's see what 16 has to offer. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? All right. You can have a high pH with purely dissolving a base, right? But do we have any like that? No. All we've got is a strong acid, a weak acid, and then salts. So the strong acid and the weak acid are going to have acidic pHs, more than likely. Well, we're given a 0.1 molar solution. That's important. 0.1 molar solution, yeah. You're going to have strong acid and weak acid are going to have acidic pHs. How about the potassium salt of a weak acid? Yeah, remember the rule of thumb? When your salt is formed from a strong base, and it doesn't say what the weak acid is. Let's just use acetic acid. That'd be a good example. When you form the salt from that one, you get KC2. Then when you take this and put it in solution, what does it do? Well, it breaks up into that ion, which is a spectator, and this strong conjugate base. That strong conjugate base reacts with water. Right? Takes a proton, reconstitutes the weak acid, and leaves behind hydroxyl. Now that's the chemistry. The rule of thumb is salt from a strong base, weak acid gives you a basic solution. But this is why. The reason it gives you a basic solution is not because of this, it's because of that. Okay. And then the potassium salt of a strong acid, that's from a strong base and a strong acid, that's a neutral solution. The ammonium salt of a strong acid, all right, that's a strong acid and a weak base. So that's going to be acidic. So the answer is C. Let's see. Does 19? Yeah, 19 is select the answer that best describes an aqueous solution made from each of the following substances. All right. Well, maybe we can do. Shouldn't take too long to do all of them, actually. I don't have mark, but nothing says we can't do it. Okay. So, sodium nitrate. That's formed from strong base, strong acid. It's going to be neutral, right? How about sodium carbonate? Sodium hydroxide is a strong base. Carbonic acid, right? That's you drink every time you swallow a pop, is a weak acid. Right? So a weak acid and a strong base, that's a basic solution. And the last one, ammonium acetate. Acetic acid and ammonium ion are both weak. So we have to, that's why we're given the Kas for each one. Well, actually the Kb for the anion and the Ka for the cation are equal. Since they're equal, the Ka is of the acid is equal to the Ka of the base, then you get a neutral solution. That's the one example that I was giving you in the lecture where you can't qualitatively assess the acidity or basicity. You need to compare the Ka and the Kb's. In this case, they're equal. So your solution is neutral. All right, number 20. Solid ammonium perchlorate. Let's see, Ka for ammonia and Kb for chlorate. Oh, okay. So we are comparing one where the ammonium chlorate perchlorate. Let's see, perchlorate, ClO4, and that's a minus. So this solid compound, when you put it in water, produces ammonium ions, and that very weak. Let's see. Yeah, this is a weak conjugate base because perchloric acid is extremely strong. That's why the Kb for this one is 10 to the minus 21. It's a very weak base. This is a stronger acid. This solution should be acidic. 10 to the minus 10 versus 10 to the minus 21. Okay, are we good? All right. Okay, 22. Which factor listed below is most important in determining the strength of an oxyacid? What's an oxyacid? Well, you have to have at least one proton, sometimes 2 or 3, but at least one. And then you have an oxygen in between the hydrogen and some other element. Like a halogen, maybe. And this can be several oxys. Right, so how does that affect the acidity? Does it affect the acidity? Which factor is most important? Size of the molecule? Ability of the molecule to change atomic orientation? That's kind of strange. Identity of the central atom in the molecule. That does have an impact. Right, that central atom, this one right here. But is it the most important? No, it's the number of oxygen atoms. The oxygen atoms are closer to the hydrogen. And the, I just had the right word and it just flew out of my head. Maybe it'll come back to me. Because when you have this in the middle and you have these several oxygens, say we have 3 of them, actually 4 of them, and then we have this hydrogen, then they have a tendency to draw electron density away from the hydrogen and weakens that bond. That makes it a stronger acid, the weaker this bond. So the more oxygens you have, stronger the acid. 24. Induction. That's it. It's an inductive effect. Which of the species below, when dissolved in water, will not produce a basic solution? All right. What's the first one? Sulfur dioxide, ammonia, barium oxide, barium hydroxide, and none. So which one will not produce a basic solution? Well, obviously this is going to produce a basic solution because it's already got the hydroxyls. Right, so Arrhenius, this is an Arrhenius base. It has the hydroxyl built into the molecule. So this is basic. How about this one? What happens when you react this one with water? It transfers hydrogen ions over there and makes barium hydroxide. That's it. There's nothing left over. Right? And then that dissolved in water produces the basic solution. Right? So the rule is metal oxides produce basic solutions in aqueous environment. This one goes in solution, it definitely produces basic. Right? That's ammonia. How about this one? When it reacts with water, what does it produce? That's acidic. Okay, so non-metal oxides in solution produce acidic solutions. That does not produce a basic solution. All right. 25. All right, which of the following species cannot act as a Lewis base? What's a Lewis base? All right. How about, well, by definition, a Lewis base is an electron Lewis base. Electron pair donor. Okay, and I always go back to the Bronsted-Lowry examples. Say like this one, sodium and hydroxide. Right. This is a positive, that's a negative. So when this goes into aqueous solution, we get the hydroxide with its, actually it's got 3 pairs of electrons. It forms a bond with one of these hydrogens, right? So it produces water. It donates that pair of electrons. That's what makes this a base, a Lewis base. So which of the following cannot act as a Lewis base? Which one cannot donate an electron pair? Right. So we have our examples, B, C, D, E. Right, first one is O2. Excuse me, O2 minus. O2 minus. Does it have lone pairs? Oh, yeah. It has 4 of them. So that would be an excellent base, Lewis base. I already did the hydroxyl. I should know that one's a Lewis base. How about this one? CH4. The Lewis, draw the Lewis structure for this one. Any lone pairs there? Nope. That would be a lousy Lewis base. H2S. H2S is like water. Right? It's got a couple of pairs there. And then ammonia. Right, has a lone pair right there. So this is the only one in that group that does not have, let's see, let me be consistent. That does not have a donatable pair of electrons. It cannot be a Lewis base. All right. So that means C for 25. Twenty-six. Which of the following species cannot act as a Lewis base? Oh, there's another one. All right. Well, they're all hydrides of, well, except for the top one, that's azide. But each one of those, A through D, has at least one lone pair to donate. That makes it a Lewis base. Right? The more negative is, the more lone pairs we have. Right? So we know ammonia can donate a lone pair. So NH2 minus, it's got an extra pair. NH2 minus, NH2 minus, and N3 minus all have extra electrons they can donate. So they're A through D are Lewis bases, whereas ammonium already has used up. Let's see, let's get rid of that. You have too many hydrogens in there. Right? There are no lone pairs with that one. That's why it has a positive charge. We used up the lone pair that we had here for ammonia and formed the bond here, coordination bond with hydrogen.
And you said the more negative, what?
More lone pairs of electrons, unbounded pairs of electrons. That's characteristic of A through D. All of those examples have extra pairs of electrons they can donate. That makes them Lewis bases. All right. Now we're going to shift gears to Lewis acid. So if a Lewis base is an electron pair donor, a Lewis acid would be an electron pair acceptor. So out of these choices, let's see, we have that one. Can it accept a pair of electrons? Oh, yeah. It's a negative charge. I mean, positive charge. It can suck up electrons like nobody's business. Magnesium, even better. Right? It's a Lewis acid. Aluminum, right? We're going from sublime to ridiculous. You can add electrons to that till cows come home. How about this one? Right, positive charge. It will accept electrons. How about this hydride ion? Nope. It's got all the electrons it can stand. Right? It's only got a 1s orbital, and it's got electrons in both of those. So you would be hard pressed to force this thing to act as a Lewis acid. Probably got some poor graduate student out there working on it though. But for our purposes, that's not a good Lewis acid. That hydride ion, that anion. All right, I kicked this one out. I don't remember why, but doesn't matter. All right, number 30. Given the following values of pKa, determine which is the weakest base of the answers listed. All right. So we have A, B, C, D, E. So we have chloride down here, fluoride. We have HCO minus. That's formide. and hypochlorite and chloride. Okay. If the pKa's for the acids, pKa's for their respective acids are, let's see, it would be this one, 1.95, and for this one, it'd be 7.54. And for this one would be 3.74. For this one would be 3.17. And for this one, it's infinite, right? Because it's from a strong acid. It's too high to mess with. All right, so which would be the weakest base of the following? The weakest base is produced from the strongest acid. And the strongest acid here is right there. That makes this the weakest base. Okay. Did I lose anybody? No? Okay. What would be the, would make the strongest base out of that group? The strongest base would be from the weakest acid. Okay. This would be the strongest base because it's the weakest acid. Right. The strongest acid is the lowest pKa. Right, so the next strongest acid would be this one. The next one would be this one, followed by that one, and then this one. This is the weakest acid out of that group. So it would make the strongest base, the strongest conjugate base. This would be the strongest conjugate base right here. All right, let's see. Go down to 38. Carbonic acid is a diprotic acid, H2CO3. Its first K is 4.2, 10 to the minus 7. Its second K is 4.8 times 10 to the minus 11. The ion product for water is 10 to the minus 14. Okay. What is the OH minus concentration of a solution that is 0.18 molar in Na2CO3? All right. Let's see. If we're going to dissolve sodium carbonate, sodium carbonate. We're going to dissolve sodium carbonate in water. It produces these. Right? Okay. And it's completely soluble. So if we start off with 0.18 molar, 0.18 molar here, this is initial. Let's just change that. This is before. So what do we have after? Well, all that's gone. Now we just end up with 2 times this 0.36 molar sodium ions and 0.18 molar carbonate, because it's 1 to 1. So we've got this concentration of carbonate ions in solution. So what reaction are we going to see with that? We're going to see carbonate plus water. And that's going to give us, you know, we might, no, I better do it step at a time. Let's do it step at a time. HCO3 minus plus OH minus. So what's the KB for that reaction? Well, we need the Ka for this one. The Ka for this one is the second Ka, 4.8 times 10 to the minus 11. So 4.8 times 10 to the minus 11. And we have 1 times 10 to the minus 14 equals KB. Actually, we're going backwards, but let's keep the numbering system correct. Right, this is KA2, so let's make this one KB2. So what would that value be? That, and then 4.8. So this would be, okay, my display is messed up. Let me fix it. Scientific 6. There we go. This one's 2.08 times 10 to the minus 4. So that's the KB for that reaction. Then we take this reaction, HCO3 2 minus plus water, and we get carbonic acid plus OH minus. So the KB for this one is 1 times 10 to the minus 14. And the Ka for that reaction is 4.2 10 to the minus 7. So this one is 2.38 times 10 to the minus 8. Okay. Now the question is, if we're going to find out what's the OH minus concentration, which one of these reactions is the controller of the OH concentration? Look to compare the KBs. They both produce hydroxyls, don't they? Yeah, they both produce hydroxyls. But this one produces more hydroxyls than this one. So this is the controlling reaction right here. Right there. See that? This one gives you more hydroxyls than that one does. So, everybody got that? I'll erase this one to make room. If we're going to use this reaction as our controlling reaction, now we can use our ice table. So our initial concentration here is 0.18 molar. There and there. What's the change? Well, we're going to lose some of this, right? Yeah, we're going to lose a little bit of that. And it's going to show up over here. So this is 0.18 minus X. This is X, and this is X. Okay. So what's the KB equal to? Well, the KB is equal to this one times that one divided by this one. So 2.08 times 10 to the minus 4 equals X times X over 0.18 minus X. Okay. Now, can we ignore that X? All right, this is 10 to the minus 4. I think we probably can ignore that X. So we're going to say this approximates X squared over 0.18. Now, this one times that one equals X squared.
You do the 1.8 times the 2.
2.08, yes. Right. And then the square root of that value should give us X. You get 6.12 times 10 to the minus 3 molar. Is that one of our answers? Yeah, that's A. All right, so what was the method here? The method is stoichiometry followed by equilibrium. stoichiometry says when this goes into solution, you produce this amount. Then you go to equilibrium. Equilibrium of that one looks like this. Equilibrium of the other one I've erased. And then to figure out which one is dominant, you need to find out which one has the largest KB, because this is a base reaction. It produces hydroxyls. So you need the KB. You can't work from Ka. All right. All right. So let's go to 39. All right, calculate the pH at equivalence for the following titration. Yeah. Question? Oh. Oh, on the work problems? Ooh. Uh-oh, I must have given you an earlier copy. Does your 39 look like this? Work problems. You got the work problems there. I think that's what you're talking about, right?
I don't have them. She don't have it on her.
Oh, it's not on your copy. Oh.
I don't have it on.
Okay,
I have it.
okay. You must have gotten an earlier version. You two got an earlier. How about you got 39? Okay,
Is that the last one?
Yeah.
yes,
I can just write it. It
okay.
don't look like it's much.
Okay, calculate the pH at equivalence of the following titration. 0.1 molar HOCl. So we have HOCl is being titrated with sodium hydroxide. Okay. The K for hypochlorous acid is 3.5 times 10 to the minus 8. Okay. And we're starting off with 0.1 molar. 0.1 molar. So if we're going to equivalence, look at the stoichiometry here. It's 1 to 1, right? 1 to 1. So we're putting both of these together, okay, and making sodium, we're making bleach plus water. Okay, that's the stoichiometry. So when we reach equivalence, right, this is before, this is after we reach equivalence, then we've used up all of that, we've used up all this, we produce 0.1 molar of that, which means what? Sodium is a spectator. So this is 0.1 molar that. Okay. Now we can do equilibrium. So the equilibrium says that this in solution produces HOCl plus OH minus. All right. Now we can set up our equilibrium, but this is a base reaction. That's a Ka, so we need the Kb for that reaction. Kw divided by Ka. That's the value we need for this reaction. And I get 2.85, oops. Round it, let me round it. 2.6 times 10 to the minus 7. Actually, it should be 2.9 because I've only got, but I'm gonna add a decimal in there so we don't have any rounding errors. All right, so when we're starting off here, we have 0.1 mole. Water doesn't count because it's pure liquid. And we have 0 here and 0 there. Okay, so the change is going to go that direction. Minus x, plus x, plus x. So we have x here, and 0.1 minus x. So this KB is going to be 2.86 times 10 to the minus 7 equals x squared over, and I'm going to go ahead, since that's 10 to the minus 7, I'm going to get rid of that x. Did I lose anybody with that? Okay. So now just 0.1 times this is 2.86 times 10 to the minus 8, correct? 10 to the minus 1 times 10 to the minus 7 is 10 to the minus 8. That's equal to x squared. So x is equal to, we want the pH. So this is going to give us hydroxyl ion concentration. Square root of that value. Oops. Okay, I get 1.69 times 10 to the minus 4 POH equals the negative log of that. It's 3.77, and pH equals 14 minus that. So I get 10.2. Close. Pick the best answer. Okay, that's all chapter 14. Yes. So now let's go get that out of my way. What's that up there? Good. Didn't have to do any specials. Let's boost that one up a little bit. Now we can get on chapter 15. Unless you have a question. Chapter 15. And where are we starting? We're not starting with number 1. Starting with number 4. Okay. A weak acid, HF, is in solution with a dissolved sodium fluoride. If HCl is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? All right. So we have sodium is a spectator. So what we have is a reaction where HF, well, it reacts with water, but it produces like that, like that. So we had some of this from sodium fluoride and some of this from the acid. And if we add extra hydrogen ions, what will react with the hydrogen ions to consume them? That's basically what the question is. If you add these, then that fluoride is going to react with those hydrogens. Because if this is a weak base, weak acid, that's a strong base. So that strong base is going to suck up the hydrogen ions. All right. Number 5. Which of the following is true for a buffered solution? All right. The solution resists change in its hydrogen ion concentration. Yeah, I'll go for that. That was A. B, the solution will not change its pH very much, even if a concentrated acid is added. Within reason, right? As long as you don't exceed the buffer capacity, yeah. The solution will not change its pH very much, even if a strong base is added. Right? Flip side of that coin. If you add a strong base, it's not going to change the pH very much. And D, any hydrogen ions will react with the conjugate base of a weak acid already in solution. And that's true also. They're all true. All right. Number 8. How do the pHs of buffered solutions compare? The pH of buffered solution, we're comparing the buffer solutions 1 and 2 above. All right, so buffer solution 1, BS1, is 5 molar acetic acid. That's what HOAC means, acetic acid. It would be the same as this, right? That's abbreviation. And then it also has 5 molar sodium acetate. And buffer solution 2 has 0.5 or 0.5. 0.5 of acetic acid and 0.5. So what does this mean? This means that you've got OAC minus the conjugate base of that acid is equal. And the same for this one. Okay, so what does that mean? That means you're right smack dab in the middle of the buffer zone. Right? Remember from Henderson-Hasselbalch equation? I can do better than that. pH equals pKa plus log of base, in this case would be OAC minus divided by acid. If these two are equal, then the pH equals the pKa, and you're right in the middle. Right here. That's where the conjugate base and the acid are equal in concentration. This is the equivalence point. This is a half equivalence point. So that is in the middle of the buffer zone. So both of them are going to give you exactly the same pH until you do something to them, right? If you add acid to this one, it's going to peter out quicker than that one. Has a lower buffer capacity. So C is the answer. The pH of both, they're equal. Let's see, how about number 9? Which of the following is the net ionic equation for the reaction that occurs during the titration of nitric acid with potassium hydroxide? That's easy. Nitric acid, right? Nitrate is a spectator. Potassium hydroxide, that was it, wasn't it? Yep. Potassium's a spectator. That's it. That's the net ionic equation for all acid-base reactions. All right, number 10. Okay, in the titration of a weak acid with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. So the stoichiometric pH is approximately 10. All right. Which of the following indicator acids would be the best to use to mark the endpoint? So the endpoint, you want the change from, remember, when you have an indicator acid, like this, it's in equilibrium with that side and this side. So if you have equal amounts of this and this, you're at the buffer pH for IN minus and HIN. Right? The key to using an indicator is color change. So if you, and typically the human eye sees a ratio of 1 to 10. So if you had 10 times as much this as you do that, so IN over HIN. If this is 10 to 1, you'll get one color. This will be the basic color. If you go the other direction, 1 to 10, get the acidic color. That's why we say that the indicator, the best indicator for reaction is where the pKa is within 1 pH unit of the stoichiometric point for your reaction. The stoichiometric point is pH 10. So the best one for this one would be between 9 and 11. Right, the Ka is between 9 and 11. So let's see, pKa is between 9 and 11, which would mean what? 10 to the minus 9 to 10 to the minus 11. So which one is close to that? I say B. Right, B is 10 to the minus 11. That would be your best choice. Okay. Thinking about it. Oops. Yeah, that's everything. All right, number 10. And scroll, 13. Which of the following solutions would be described as a buffer solution? What do you need for a buffer? You need two things. You need a weak acid and its conjugate base in roughly equal amounts. Okay? So let's see if we can eliminate any in here. How about E? Hydrochloric acid, sodium hydroxide. It doesn't matter how much of each one you put in there, you're not going to make a buffer because hydrochloric acid is strong. So if we're working our way down, there are choices. E can't be it. How about D? Ammonia and sodium hydroxide. That's two bases. You add two bases together, you're not going to get a buffer. Okay. How about C? Sodium bromide and hydrobromic acid. That's the salt and the strong acid. HBr is a strong acid, so that one's out also. You got to have a weak acid. So A and B are possible. CH3COOH. CH3COOH. What's that? Acetic acid. It's HC2H3O2. Same formula. Just written differently. It's written, did I show you this in class? It's written this way because it gives you a little bit of information about the structure. There's your methyl group right here. Then it's attached to this carbon, and that carbon has an oxygen here, an oxygen there, there, that's your acidic hydrogen right there. That's why they write it that way. Okay, so A and B are possible because you've got a weak acid, but the first one, you've got a weak acid and a strong acid. That'll never happen. So process of elimination, B is the answer. And we check ourselves, right? You've got sodium hydroxide added to 0.25 molar C3 acetic acid. That wouldn't be a good buffer, but it would be a buffer. Right. So out of those 5, that's the best choice. Not the best buffer, it's just the best choice. $14. Yep, 14. All right. Which of the following mixtures would be classified as a buffer solution? All right, so we're going at it again here. All right, so let's do our elimination again. A is a strong acid and a salt of the strong acid. That'll never work. You got to have that weak acid in there. Or you need a weak base and it's conjugate acid. That would also work. Let's see. The second one is acetic acid and sodium hydroxide. That's possible. The problem is if you add 55 milliliters of 0.1 molar sodium hydroxide and 50 milliliters of acetic acid, you're past the stoichiometric point, right? You've neutralized that acid completely. You're not in the buffer zone. All right, so B can't be in either. You've used it all up. Right? You're on the steep part of that titration curve now. C is 0.1 molar acetic acid and 25 milliliters of sodium hydroxide. That's a good one. Why? Because they're equal concentrations of acid and base, but you're only using half the base. That means you've neutralized only half of the weak acid to produce an equal amount of acetate ion. Did that one fly over your head? No? Good? Okay. So C is the best buffer out of that bunch. We can look at D and E and say they're bad. Well, D, there's not enough base, right? 0.5 milliliters and 50 mil. You're not even into the buffer zone yet. Nowhere near it. So D can't be it. And E is, you're adding acid and acid. That'll never work either. So C is the best answer. It all goes back to that ratio, right? The closer you can get to 1-to-1 conjugate base with the weak acid, the better you are for your buffer. How about 19? Consider the following indicators and their pH ranges. All right, so we have methyl orange, methyl red, bromothymol blue, phenolphthalein, alizarin yellow. And the pH, the actual pH ranges for their color changes are given. We're not using the rule of thumb, plus or minus 1. Those are the actual pH ranges determined for each one, the useful ranges of color change. So, for which of the following titrations would methyl red be the best indicator? Methyl red is 4.8 to 6. pH 4.8 to 6.0 is the best range for that one. Okay, so what does this mean? Well, if we're going to compare that to KAs or KBs, we need to know when do these reactions reach stoichiometric equivalence? I'll try to stay on track here. All right, well, let's see if we can eliminate the easiest ones. 0.1 molar HNO3 and 0.1 molar KOH. That equivalence is going to be at pH 7. Right, strong acid, strong base, put them together in equal amounts, and you get a pH 7. So that's outside this range. pH 7 for this one is the stoichiometric point. Can we say anything about B? Aniline, which has a Kb of 3.8 10 to the minus 1, and HCl. Okay, when it reaches stoichiometric equivalence, we've got a weak base with a strong acid, and that titration is going to look different. Like if we're going to add strong acid, then it's going to start up here. Right? And it's going to go, let's see, it's going to go like this, and then like that, and then like this. So its equivalence is going to be out here somewhere. The Kb, 3.8 times 10 to the minus 10, negative log of 3.8 times 10 to the minus 10 is what? $9.4. This would be 9.4 right here. And that's only half equivalence. So let's see. Can we predict where this one's going to be? Yeah, we should be able to. If we say aniline, plus water is going to yield HAN plus OH minus. Okay. So if we're starting off with, let's see, 0.1 molar of each one of them. So this is going to be you know what? This is the PKB. What's PKA? That'd be 14 minus that, wouldn't it? Let me see if I'm right. The PKA for this one would be 1 times 10 to the minus 14 divided by 3.8 times 10 to the minus 10. And that's equal to 2.63 times 10 to the minus 5. So the PK, excuse me, that's the K. The PKA then would be the negative log of that. Um, 4.58. 4.58 plus 9.4. Yeah, okay. I'm just checking myself. If we can do POH and pH, right, subtracted from 4, then we can say the pKa for water is 14. Subtract the pKb and you get pKa, 4.58. So why do I say that? Because if this is, let's see, 0.1. 0.1 molar. Yeah. If this is 0.1 molar, that's 0, 0. And then the change minus X plus X plus X. And then at equilibrium, we have 0.1 over minus x. This is x, this is x. I'm trying to figure out an easy way to do this, but I think I'm gonna have to do it the hard way. This is PKB, so PKB is here, 9.4. Actually, we need the KB. This is KB right here. So KB, 3.8 times 10 to the minus 10 equals x squared over 0.1. Okay, so x is the square root of 3.8 10 to the minus 11. 6.2 times 10 to the minus 6. That's equal to hydroxyls. So POH is the negative log of that. 5.2. And the pH is equal to 14 minus that. 8.8. All right, what we're saying is at equivalence, this is 8.8. All right, so at equivalence, our value here is pH 8.8, right? That's too big, right? This methyl red won't work for that reaction. I was trying to use a Henderson Hasselbalch, but it didn't work. So, everybody got that? Okay, I'll erase this. So the short version is, for the first reaction, its stoichiometric point is 7. For this reaction, the stoichiometric point is 8. For C, the stoichiometric point for ammonia and hydrochloric acid, right, is still 0.1, 0.1. So actually, we can make this pretty simple. We've got the same setup here. The PKB for this one, the KB, excuse me, the KB is equal to 1.8 times 10 to the minus 5. 1.8 times 10 to the minus 5, which is equal to x squared over 0.1. Right? They're all the same concentration, so we can just duplicate it. We just change this value for each one. So this is going to be 1.8 exponent minus 6 because we multiply it by the 10. And I'm going to take the square root of that. Here's 1.34. X equals 1.34 times 10 to the minus 3, which is the hydroxyl ion concentration. Right? So POH is the negative log of that. .87, and the pH is 14 minus that, or 11.1. So this one, the pH at equivalence is 11. That doesn't make sense. KB. I did something wrong. What did I do? Oh. C. No, that's KB. KB plus the acid. Oh. My mistake. We're working from a different, let me leave that there for now. All right, so for ammonia, at equivalence, we're going to have only this, right? And that's going to be the equilibrium, right? I made a boo-boo. That's going to be the equilibrium for ammonia. So ammonia, I wonder if I did B right. No, I didn't. I did B backwards. Still B is wrong. I mean, B is not the best one, but I did it backwards because at equivalence, okay, I broke my own rules. You're supposed to go stoichiometry first, then use those values for equilibrium. So now we have what? Well, now we have initial, this amount. Is it 0.1? No, because we've added equal volumes. Okay. Let me do this one the long way. When we add equal volumes of ammonia and acid, we have 0.1 molar of some volume X milliliters, X milliliters. And then we add the acid at 0.1 molar at the same number of milliliters, right? Same concentration. So what's the concentration of ammonia after this reaction? Well, it's 0.1. It's half of that, right? Because you get equal volumes diluting 0.1 molar. So this one, our starting initial concentration is 0.05 molar. So when we get down to equilibrium, now we're going to have 0.05 minus X and X and X. Okay, so now we have we got to find the K. We got to find the Ka. 1.8 times 10 to the minus 5 is Kb. So Ka equals 1 times 10 to the minus 14 over 1.8. 1.8 times 10 to the minus 5. There we go. Or 5.6 times 10 to the minus 10. All right, that's the value for Ka. That works for this one because this is an acid dissociation. All right, so this value is equal to X squared approximately over 0.05. I think while you were gone, I explained the concentration here is cut in half because we're titrating ammonia with acid, equal concentrations, so it takes equal volumes. That means we double the volume and we cut the concentration in half. So that's where we are now. This is the Ka because this is a Ka expression, not a Kb. So I found the Ka from the Kb for ammonia. And that's equal to this. I multiply 0.5 times 5.6, 0.05, and then take the square root of it. So this is hydrogen ion concentration equals 5.27 times 10 to the minus 6. And pH equals negative log, or 5.3. Okay, 5.3. 5.3 pH. There it is right there. That's why C is the answer. My fear is that bouncing around like I did, I've confused everybody.
I was, yeah. So you do the 5 point, how did you get to 5.2?
Here.
Yeah.
0.05 times 5.6 times 10 to the minus 2, square root of it. This is an equation here. That equals this.
You do the 5.6 times.
Times 0.05. Then take square root.
It's 2.0.
They give you this value. Let me be sure I did it right. Let's see, I had to find the Ka first from the Kb. So 1, it's 114, it's 1.8, 5. Okay, 5.6, 10 minus 10, that's correct. And then I multiply that times 0.05. It's 2.78 times 10 minus 11. Okay, then the square root of it. Square root is 5.3 times 10 to the minus, okay, that should be a 3. 10 minus 6, and then I take the negative log of that. It's still 5.3, rounded off.
Okay, I got it. It worked.
We use that same reasoning for the rest of them. Because it looks like, well, HF, you don't have to do the conversion because the Ka is already there. But when we reach equivalence, no, you do need the Kb. For HF, for the D, say, express this, for the D, the before is HF plus hydroxyl, is it? Yeah. Yields F minus plus water. So this is going to be 0.1 molar. This is 0.1 molar. And this is before and after. All this is gone. And we end up with 0.1 divided by 2 molar. Because we get the same stoichiometry, the same number of moles on this side as that side. But when you're at equilibrium, when you're at stoichiometric point, you got twice the volume. So that's why we divide by 2. Now we've got 0.05. And the fluoride ion in solution, fluoride plus water, yields HF plus OH minus. And this is, the beginning is 0.05 molar. That's 0, that's 0. And then at equilibrium, we have 0.05 minus X, and this is X, and this is X. So then you set up that same arrangement, but we need the Kb for HF. We got the Ka, so we need 7.2 times 10 to the minus 4. 4 divided into 10 to the minus 14. Okay, so the Kb for this reaction, right? It's got to be Kb because you've got a conjugate base here, reacted with water gives you OH minus. So that's a Kb. And this is 1.4 times 10 to the minus 11. That is equal to X squared over 0.05. And we can say that because this is so small. Then you say 0.05 times that one. Let's see, 0.5 times that one, then take the square root of it. And I get X equals 8.3 times 10 to the minus 7. And that's the hydrogen, the hydroxyl concentration. So POH then is negative log of that, 601, 6.1. And the pH then is 14 minus that one, 7.9. Right, so that's too big. D doesn't work because it's past that value. That number 19 takes a lot of work. Let's go to 23. Okay. 50 milliliter solution of 0.035 molar hydrocyanic acid titrated with 0.033 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 milliliters of titrant have been added? Okay, so we're giving you a hint. We're saying it's acidic solution because we haven't completely neutralized. So let's put what we know. The reaction for the titration is hydrocyanic acid. And sodium hydroxide, right? Is that right? Sodium hydroxide? Yes. And that yields, actually, for this part of the reaction, we're going to say it does that. So this is sodium cyanide plus water. Okay, what are we starting off with? Hydrocyanic acid is 0.035 molar. 0.035 molar, 50 milliliters. Correct? Yes. Is titrated with 0.0333 molar sodium hydroxide. 0.033 molar sodium hydroxide. Let's see. What's the pH after 15 milliliters of titrant? So this is 15 milliliters. Okay, that's given. All right. So what we have to do is find out how much of this is produced and what's left over here. So the best way to do this is to find out how many millimoles. We're going to do a stoichiometry problem first. Milliliters times molarity is millimoles, right? So 0.035 times 50 is 1.75 millimoles. 0.0333 times 15 is 0.4995 millimoles. Okay. All right. So this is before. And what do we have after? Well, this strong base is completely consumed because there's plenty of acid left available. So this is going to 0. And what do we have left over here? It's 1 to 1. So 1.75 minus 0.45 is what we have after. $1.25 rounded off millimoles. All right, what do we have on this side though? Before we had 0. Now we have what? Well, we've used up all of this, right, to produce an equal amount over here. So this is 0.4995 millimoles. And water doesn't count. Okay, so that's the stoichiometry. Now, in order to do the equilibrium, we have to know the concentration. So what's the concentration that we're gonna start with. We still have some hydrocyanic acid. And that is in how many milliliters? 65 milliliters, right? 50 plus 15. Millimoles divided by milliliters is equal to molarity. And I get 1.92 times 10 to the minus 2 molar. And this one is also in 65 milliliters. 0.45 enter 65. This is 7.68 times 10 to the minus 3 molar. That's where we start with our stoichiometry. The nice thing about this is we can use Henderson-Hasselbalch now because we know what the conjugate base concentration is and we know what the acid concentration is. But Henderson-Hasselbalch needs Ka, and we've got Kb, 3.2 times 10 to the minus 5. So the Ka equals 3.2 times 10 to the minus 5. And this is 1 times 10 to the minus 14. So we do 1 exponent 14 there, divide by 3.2 exponent minus 5. So this is 3.13 times 10 to the minus 10. That's Ka. Now that we have Ka, we've got the acid concentration, we got the base, conjugate base concentration, we can use Henderson-Hasselbalch. So pH equals pKa plus log of conjugate base over the acid. And that means, well, we have to do negative log of this. Negative log of 3.13 times 10 to the minus 10 plus the log of 7.68 times 10 to the minus 3. That out of the way so we don't. There we go. And then HCN was just what I erased. What was the value?
So 1.9.
Yeah, right. This one right here.
1.92.
Yeah.
Times 10 to the negative 2.
Thank you. Okay, so the pH is going to be whatever this resolved to. 3.13 negative log of that one. Log, change sign. So this is 9.5. And this is 7.68 exponent 3, change the sign. Divide by 1.92 exponent 2, change the sign. Divide. And then I get 0.4. Yeah, 0.4. Take the log of that. And that's minus 0.38. So that, and I get 9.1 pH. That's not it. What did I do wrong? Okay. I made a mistake here. Is this right? 3.2 10 to the minus 5. No. Where did I get that number? 6.2. Oh, the Ka is already given. What am I doing? We've already got the Ka. That's the wrong value. Right, sorry, guys. HCN, Ka is 6.2 times 10 to the minus 10. Take the log of that. And minus, yeah, 9.2. There we go. I think this one is correct. This is 8.8. There we go. That's it. Seems sometimes I'm my own worst enemy. I misread that. I must have been, oh, I was looking at 24. Just look down below. 3.2 times 10, that's 5. It's looking at the wrong problem. Okay. You feel good with the method? Right? Before, after, once you get the after, if you're not at equivalence, then you can use Henderson-Hasselbalch to go the rest of the way. And that really simplifies things. All right. 25. I've got to make a disclaimer. I know what the authors of the problem want us to do, but the way it's worded, we can't do it the way they want us to. Now, the way I did it in the work problems, I think I did it the way they want us to. Let's see. Yeah, I did it the way they wanted. I'm going to do it the way it should be done and show you the difference. So a certain indicator has a pKa of 9 and a color change becomes visible when 7% of IN minus, when it is IN minus, 7% of that is IN minus. All right. At what pH is the color change visible? So our reaction here is this one I showed you earlier. And the pKa of this one is 9. All right. 7%. So what would be the equilibrium concentration? If this is 7% or 0.07, what's left over? 0.93, isn't it? Right. If we've used up 7% or 0.07 of the total, and the total is 1, then 1 minus 0.07 equals 0.93. So the ratio is 0.07 to 0.93. If we use Henderson-Hasselbalch 9.0 here, plus the log of this ratio, 0.07, and in the denominator, it's 0.93. Right? The authors of the problem want you to put 0.07 right here. Right? But if we've used up 0.07 of it, that's what's left. That's my issue with the authors. So 0.07 divided by 0.93 is 7.53 times 10 to the minus 2. Take the log of that. And that's minus 1.12 at 9. So that's equal to 7.9 pH. Close. It doesn't make a whole lot of difference, but if we want to be accurate, we'll take them at their word. Not what they want, what they ask for. I think it just worded the problem wrong. Can't get that answer?
I don't get the 7.53.
0.07 divided by 0.93. Anybody else doing that? See if you get the same value.
Try that.
Okay, then take the log of it, and I got this. And that plus 9 is 7.9. Actually, 7.88. Right? Right, because this is two significant figures here. I expanded that one a little bit, but I can have 2 decimal places in the pH. Right, so 1.12. So that's actually, this is a better 7.88 rather than 7.85. So I need to change that. All right, is this the last one? Nope, we got more. Okay, we're coming up on 11. All right, 26. We're close to the end.
Well, 3 more chapters after this.
Is that all?
Yeah.
Wow.
Counting it down, are you?
It's the same one.
Okay, in this figure below, all right, this one right here. So let me put 26 and 27 and what we're looking for. In 26, we're looking for the pH at first equivalence. pH at first equivalence. Okay, at 27, we're looking for best buffer pH. And we have, let's see. Well, let's see, the answer we're given here is 6.02, right? 6.02. And the answer we're given here is 10. That's so I don't have to shrink everything down. So let's go see how we got those values. I am gonna have to shrink a little bit. All right, so we have base added on the x-axis and y-axis pH. So we're looking for this one, the pH at first equivalence. Where does that occur? First equivalence occurs in the steepest part of the curve, the first one you come to. That's the point C. Right? So the nearest answer to that one is 6.02. All right, that's the first equivalence. Second equivalence would be near 12, be 11.8 or 11.9. That's second equivalence. So this is a diprotic acid. You can tell that from the titration curve. Okay, how about the best buffer pH? Well, of the ones we had to choose from, 10 was the best, D. Right, that D position is close to 10. That's the best buffer. Now, if you had other values given, then the first buffer position would be at B, about 2.5 or 2.4. Okay, those are the buffer positions. All right, takes care of those two. Oh, that's it.